Okay guys, so here's our first rotation problem, or set of problems. We've got a bucket. We're rotating the bucket on a 1.5 meter rope in a vertical circle. It's turning 5 times in 2 seconds. It's moving in a uniform circular motion, which means its speed's not changing. It's accelerating because it's spinning, it's changing direction, but its actual rotational speed isn't changing. We want to find the period, the frequency, the angular displacement, the linear displacement, the angular velocity, and the linear velocity, or sometimes that's called the tangential velocity of the bucket. So let's go to a slide where we have some space, and we'll find these things. The first thing we were asked to find was the period. Remember that the period, capital T, is the time it takes for one revolution or one rotation. And it tells us in the problem that the bucket spins around 5 times in 2 seconds. For period, what we're trying to find is how many seconds it takes for one time. So if we take 2 seconds divided by 5 revolutions, 2/5. So we end up with 0.4 seconds per revolution. That's our period. That's capital T. Frequency was the next thing we were asked to find. There's 2 ways we could find this. One equation that you ought to know by now is frequency is 1 over the period. The definition of frequency, though, is how many revolutions or rotations per second. How many of something per second? It told us that it goes 5 times in 2 seconds. So one way we could find that is to say 5 revolutions divided by 2 seconds and end up with 2.5 revolutions per second, which often gets written as hertz, 2.5 hertz. Or we could have said 1 divided by 0.4. We've still got the same answer. So this is our frequency. This is our period. The third thing we were asked to find is angular displacement. Symbol for angular displacement is theta. And angular displacement is basically how far did we go in terms of angles around the circle. This told us that we spin 5 times. 1 time around a circle, you should know, is 2 pi radians. We're spinning 5 times around. So we're going to say 2 pi times 5. We're going to end up with 10 pi, which is 31.4 radians. That's our angular displacement, 31.4 radians. I'm going to erase a little bit here. The next thing we were asked to find was a linear displacement. The relationship we're going to use there is that distance, or we couldn't use delta x here, is equal to the radius of rotation times our angular displacement. So in this problem, the radius is the length of our rope, 1.5 meters, and the angular displacement, 31.4 rads. So if we do the math on that, 1.5 times 31.4, we end up with a linear displacement, delta x or d, 47.1. Now notice this looks like meters times radians is our unit. But since we're talking linear, we drop the radians. 47.1 meters is our linear displacement. The number 5 question we were asked is what's the angular velocity? To find angular velocity, just like regular velocity, it's displacement over time. So for this one, we're going to say omega equals angular displacement divided by change in time. So in this problem, we just found that our angular displacement was 31.4 radians. And it took us, according to the problem, 2 seconds to do that. So if we divide that out, 31.4 divided by 2, we end up with 15.7 radians per second. That is omega, our angular velocity. The final question on this problem set was, what's the linear or tangential velocity? The relationship between linear and angular is, again, linear equals radius times angular velocity. So in this problem, we're going to take our radius, 1.5, and we're going to multiply it by our angular velocity. So 1.5 meters, that's the length of our rope, times 15.7 radians per second. And we're going to end up with 23.6. Now again, it looks like our units are going to be meters times radians per second. But we're talking about linear stuff here, not circular stuff. So we drop the radians, and our answer, 23.6 meters per second. All right, the next thing we're going to do is a couple of quick conversions. We're going to convert 60 revolutions per hour, or 60 revolutions per hour at 160 degrees per minute. We're going to convert both of those to radians per second. So let's go to a slide where we have some space. The first problem was 60 revolutions per hour. And we're trying to get to radians per second. One revolution is 2 pi radians. I'm going to write that as 6.28 radians. And then we've got to convert, we're trying to get to radians per second. So let's mark out our revs. We need to go hours to seconds. So I'm going to go 1 hour is 3,600 seconds. 60 times 60. So if we do the math on that, 60 times 6.28 divided by 3,600, we end up with 3 significant digits here, 0.105. And again, that answer is in radians per second, 0.105 radians per second. The second conversion problem was to convert 160, and that's degrees per minute. And again, we're trying to get radians per second. So you know that 360 degrees is the same as 2 pi, 6.28 radians. And you know that 1 minute is the same as 60 seconds. So minutes cancel, degrees cancel. Now let's do the math on this. So let's go 160 times 6.28. Let's divide that by 360, and let's divide it again by 60. So we end up with, we need 4 significant digits on this problem. So we end up with 0.0465 blank. And again, that is in degrees per second. All right, let's backtrack to another problem. This time we've got an angular, what is the angular velocity in radians per second of the minute hand of a clock? And then the second part of that question, we want the linear velocity. Let's first find the angular velocity. We're talking about for the minute hand of clock. So here's a clock. Let's say this is our minute hand. Well, that's terrible. For the minute hand of a clock, it takes 1 hour. For the minute hand to go all the way around. So it takes 60 minutes. It takes 3,600 seconds to go all the way around. That is what we would call period. 3,600 seconds. It's the amount of time it takes for that minute hand to go all the way around the clock. 1 hour, 60 minutes, or 3,600 seconds. it goes that far, it takes it that long to go one revolution. We're trying to find angular velocity. Angular velocity is omega equals theta, or delta theta, divided by delta t. Remember that delta theta is the angular displacement. We're going to do that for one time around, which is one revolution, or we're going to write it in terms of radians, 6.28 radians, and it goes that far in a time of 3,600 seconds. So if we do the math on that, 6.28 divided by 3,600, we end up with the proper number of significant digits here, which is 3, of 1.74 times 10 to the minus 3 radians per second. That is our angular velocity, or omega. The second part of that problem was to find the linear velocity. And again, the relationship is linear velocity equals r times omega. So in this problem, we're told in the end of the problem that the minute hand is 20 centimeters long, 0.2 meters. So we're going to say 0.2 meters times 1.74 times 10 to the minus 3 radians per second. And when we multiply that out, again, it looks like we should get meters times radians per second. We're talking about linear stuff here. So we're going to drop the radians and write 3.49 times 10 to the minus 4 meters per second. That's our linear velocity. All right, let's skip forward and look at the next problem. This time we're doing a turntable problem. And look at what it gives us. It gives us the mass of a turntable. It gives us the radius. It tells us the amount of friction. And it tells us the amount of force that's applied. And we want to find the acceleration. Now, first of all, let's get to a new blank slide. We're trying to find the angular acceleration, which is alpha. And that didn't quite turn out right. Alpha. Angular acceleration. With these turntable problems, most of the time we're going to have to use the torque equations to get there. Torque is Fr, force times radius. It's also inertia times angular acceleration. Now in this problem, we have enough, I think, to use maybe this torque equation to get torque, and then use this torque equation to find angular acceleration. So it tells us a turntable has a mass of 500 grams and a radius of 0.5 meters. So we know R is 0.5. We have a frictional force of 25 newtons. We push on the force with 75 newtons. So we apply a force of 75. We have a frictional force that resists that of 25. So it's like really that we only push with the force of 50 newtons. So our F is 50. Our radius is 0.5. So we're going to say T equals 50 newtons of actual net force times a radius of 0.5 meters. So we end up with a torque of 25 Newton meters. That's our torque, 25 Newton meters. Now we're going to use this equation over here in just a second. But before we do, we need to find the inertia of our turntable. We need to find I. You have a sheet of formulas to help you calculate inertia. And if you look at those picture formula sheet, for something shaped like a turntable, the formula for inertia is 1/2 mR squared. So we're going to say I equals 1/2. Our mass was 500 grams. We won't do that in kilograms though. So 0.5 kilograms times our radius squared. And again, our radius was 0.5. So if you do the math on that, 0.5 squared times 0.5 again, times a half. So we end up with I equals 0.0625 kilogram meters squared. All right, so I'm going to make a little space here. Once again, remember we know the torque, 25 newton meters. We now know the inertia, 0.0625 kilogram meters squared. So we're going to take this number and this number, and we're going to use this equation to find angular acceleration. So solve that out for alpha. Alpha is going to be equal to torque divided by inertia. So our torque, 25, divided by our inertia, 0.0625 kilogram times meters squared. Let's divide that out. 25 divided by 0.0625. We end up with 400. It should be 400 with a decimal point. Now your units on this are going to be kind of strange. You got to remember that a newton is a kilogram times a meter over a second squared. So everything is going to cancel out here except seconds squared. So it looks like we've got 400 over seconds squared. But we're trying to go from linear to rotational here, to circular. So what we can imply to be here is a radian. 400 radians per second squared. Angular acceleration ought to be in terms of radians. The very last part of this question asks us to take our angular acceleration, alpha, and convert that over to linear acceleration. Once again, that's going to be proportional. Linear is going to be proportional to angular times the radius. So once again, our radius here was 0.5 meters times our angular acceleration of 400 radians per second squared. So we end up with a linear acceleration of 200. Again, we drop the radians, that's supposed to be a decimal point down there, meters per second squared as our angular, or our linear acceleration rather. Hey, you spooked me.
Somebody said that you...
Someone's recording this. All right, our very last problem for today, number 12, is kind of a classic seesaw problem. We've got a child of mass 70 kilograms sitting 2 meters from the fulcrum of a seesaw. We want to know how far from the fulcrum on the other side a 50 kilogram child must sit to balance the seesaw. Again, let's go to a clean slide. For a seesaw to not rotate, the torque on this side has to be equal to the torque on this side. Now we know that torque, force times radius over here, has to equal force times radius over here. So on one side of the seesaw we have a 70 kilogram child. Now realize, kilograms are not force, they're mass. So we should say 70 times 9.8 to get the weight, the force, times the distance from the center, which was 2 meters. That's got to be equal to force times radius on the other side. Well, the other kid was a 50 kilogram kid. So again, we got to convert that over to weight. And we're looking for that distance, for that radius. So if we do the math on this, let's go 70 times 9.8 times 2. And let's divide that by 50 and divide again by 9.8. So we end up with a radius, a distance from the center, r equals 2.80 meters. So that's how far the 50 kilogram child would sit from the middle of the seesaw in order to balance out the seesaw. Hope that helps.